All right, this is called Benford's Law, which is actually kind of interesting. They use this a lot to check for fraud in accounting, that they basically say, and you can kind of look at the picture here, and these numbers are given. This is Benford's Law, so you will use these exact numbers anytime you work a problem, trying to see if the majority of the leading digit. Okay, so the very first value in a list, and here the list is populations of these counties, of 120 counties, and they're saying the leading digit of these populations, 1, 2, 3, and so on. Okay, and so again, this information is set in stone. You will not change these probabilities. So they went out and they observed these populations to see what their leading digits were. And our null hypothesis is to see, does it conform with this Benford's law? So when we're given percentages to find our expected value, we take our sample size and multiply it times that probability. And in this case, these are my probabilities. So what I would do is I would take my n, which is 120. So I'm going to do an equal n. Now I want to copy this formula, so I want to always use this cell. So this is where you put the dollar signs. If you press F4 on your keyboard, that's what I did. It does it for you. But what the dollar signs mean is absolute value, absolute reference, this cell, the cell B13. So when I copy this down, it will always use the 120. It won't copy and move down as I'm copying. All right, so then times P, and I want this one to move down, so I won't absolute reference it. So I hit enter and I get that value, and then now I can copy my formula straight down. So you can see if you kind of double click on one of these, it's absolute referencing my value of n. All right, so just as we did in the first video, the goodness of fit, and in fact I can just be lazy and go copy it right here, is we used this formula that said take our observed minus our expected, square it, and then divide by our expected. So our observed minus this expected, oops, close parentheses, square, divided by my expected. All right, so the same thing we did on the last one. I take this and I copy it straight down. And as we did on the last one, to find my chi-square test statistic. So chi-square test statistic, I just simply sum these values. So that's what I'm going to use to compare, either find the p-value, which I'm going to do both, or compare it against my critical value. So I can find the p-value, as I did on the last video, by using chisq.dist.rt, and then I'm going to click on my chi-square test statistic. Now here you have to be careful. The degrees of freedom is actually these. It's not the sample size minus 1. It's how many of these values minus 1. So we can see there's 9. So minus 1 would be 8. And I close my parentheses, and I definitely get a high p-value, which is going to be higher if I choose the level of significance of 0.05. So I know right now I would not reject the null, that I would say, apparently this looks like it follows Benford's law. I could go ahead just to be complete and get my chi-square critical value to see if the chi-square test statistic falls in it. And so I use my formula, again, that we used in the last video. Click on my alpha. My degrees of freedom is 8. And I can see certainly that the 5 does not fall in this critical region. So again, I failed to reject the null, that it appears when they got this data that it does follow this Benford's law.